He's the founder of Research Lab. Namaskar, Mr. Mondal. Thank you for joining us and giving your valuable time to us. Before I begin, I would like to thank SAP for giving me this opportunity to always work with you and bring new things to the table. And looking forward to learning a lot with you guys today. I would request Gauri from SAP to introduce our esteemed guest for today's workshop. Please, Gauri, if you do the honors.
Yes, ma'am. Yes. So here at SAP, we often get like opportunities like these where we get to conduct such wonderful workshops. So of course, it's very special that we're pleased to welcome Architect Joy Mondal for taking time out and teaching us during this weekend's workshop. So just to mention a bit about him, Architect Joy Mondal leads a research lab which offers design computation consultancy to architecture practices in Southeast Asia. And he has released 2 Grasshopper plugins to automate design workflows. And he has tutored workshops across the world, including at the American University at Cairo and the Chinese University at Hong Kong, and also the University of Southern California. So hope to learn a lot from you in these 3 days. Yes, ma'am, you may continue.
Okay. Before we begin, as you know, all of you, we have a 3-day workshop planned for all of you. So there are going to be 6 sessions every evening for the next, starting from today. So the first session will be from 3 to 5, and then we have a bit of a break, and we have the second session from 6 to 8. But of course, we'll see how and when it is convenient, we will accordingly shift the sessions as per the convenience of our guest and the convenience of the students who are participating. So before we begin, I think Mr. Mondal could give you a brief idea about our today's session. So I leave the floor up to you and take it from here then.
Thank you, ma'am, and thank you, Gauri, for the kind introduction. It's lovely to be here amongst you people, and also welcome to the professors from the department as well. I've been looking forward to sort of have such a technical conversation with the department in IIT Kharagpur for a long time, and thankfully it has worked out now. The topic of this particular workshop is the use of AI and machine learning in architecture. As you guys must know, I'm going to share my screen. The schedule is such that today we're going to basically discuss, or in other words, I'm going to introduce what AI and machine learning are, and then what are the various ways in which it could be used in architecture. And then after the presentation, probably in the second half of this session itself, and in the next session, we're going to work on style transfer, which is one of the examples of the use of AI and machine learning. And tomorrow and the day after, we are going to work on a very specific idea or a very specific process of quantification of subjective evaluation of design, wherein we're going to iterate the shape of a rotating tower geometry, and then all of us are going to review how one iteration is in terms of originality or plagiarism compared to the original design. And then we're going to train a neural network to predict the originality score of new such rotating tower design options. Now, keep in mind that the steps of the process would be the same for any other exercise, wherein you may want to quantify any other kind of subjective opinion. Instead of originality, you could talk about beauty, you could talk about visual perception of safety, so on and so forth. And I'm also going to talk about these aspects in the presentation that is to follow. So we just got to keep in mind that there are 2 parts to it. The first exercise will use a pre-trained neural network. So we'll have a soft introduction to how neural network could be used. And then in the second exercise, which we're going to focus on tomorrow and the day after, we're going to collect data for training a neural network. And also we are going to train a neural network from scratch. So you're going to work on every aspect of the use of AI / machine learning in architecture or even in the broader scale. Uh, what needs to be kept in mind, I must give out a fair warning, is that the business of collecting data is the part of any exercise of employing AI or machine learning. That aspect of the process takes the highest amount of time. As a thumb rule, about 70 to 75% of the time of any project is spent in collecting data, which is also why you may sort of start and understand that why all of our phones and uh, browsing history, all of it gets tracked, because collecting data is the biggest challenge for any predictive or classification problem using AI or machine learning. Uh, so without further to do, I will start with the presentation.
Absolutely. I think we can start with that now.
Yeah. Um, I am comfortable in English, Hindi, and Bengali, so you may communicate with me in any one of the three languages. Also, while I'm going through the presentation, I may not be able to simultaneously look at the chat window. So at any slide, if you have any question, I would request do not raise your hand, or the equivalent of Microsoft Teams. I'm not sure what is the equivalent in Microsoft Teams. Unmute yourself and interject, and please go ahead and ask me the question. That will be an easier way to sort of clear your doubts, because those may end up piling up a lot by the end of the presentation. Yeah, so I run a consultancy called Research Lab, and we give design computation consultancy to architectural practices. We basically solve very specific computational problems from one project to the other. And also we release software solutions for the larger design computation community to work on. One such plugin is called Chingri, which mimics Piet Mondrian inspired 3D forms, which could be useful in conceptual designs. The other, called Elish, is actually pretty dear to my heart because it automates the placements of columns and beams on orthogonal floor plans, something that we end up repeating from one project to the other. The logic, the if-else logic keeps getting repeated. So we've kind of formalized it. It works well in the Rhino Grasshopper setup. We have to translate it into AutoCAD for it to sort of have the least amount of barrier to entry. A lot of us do not work in Rhino and Grasshopper. Anyway, having said that, this initial presentation would focus on the difference between AI and machine learning and neural network. Some of you may know the differences, but still it's better to reiterate it. Then we'll talk about the different kinds of learning algorithms. The initial examples will not be directly from architecture. Those will be just worldly examples. And then at the end, we'll talk about style transfer, and then we'll speculate what are the different kinds of uses of artificial intelligence. I must confess that, sorry, any investigation of AI and machine learning is very, very, very speculative in nature at the moment, at least in the domain of architecture and design. It is in a way similar to the watershed movement of the 1990s, where some architects, specifically led by Frank Gehry, incorporated or borrowed parametric modeling tools from the automobile and aviation industries. Frank Gehry had done that to basically digitally translate his design of the Bilbao Museum and then rationalize the form so that it could be constructed. So the speculative nature of the tools in the early 1990s, which now have sort of been formalized in the form of Grasshopper and Rhino and other plugins like Dynamo, etc. Now there are so many tutorials, so many established methods of the different software and tools talking to each other. Similarly, AI is at the 1990s stage at the moment. There's no concrete formal theory, so to speak, in terms of the use in architecture. So it could also be an invitation to you guys, because AI in architecture or design is at the moment a pretty low-hanging fruit. If you're able to conquer the technical aspect of it, making meaningful publications or making meaningful contributions isn't as difficult, because there isn't much legacy in this particular cross-disciplinary domain. So the basic difference between any parametric software or any algorithm, the traditional algorithm, compared to the use of machine learning is that in the traditional sense, or even when we write parametric scripts, what we know are the rules or the logic of the algorithm. And of course, we have input data. And using those two, we get the output or the answers. Whereas in the case of machine learning, we don't know how the output is arrived at. We don't know the backend logic. We don't know the algorithm. And so in a reverse way, we end up having a bunch of input variables or input numbers or input data and a bunch of output data corresponding to these input data. And the machine itself, of course, learns and figures out the algorithm or the logic to arrive at the output from the given set of input, which kind of makes it obvious that the more number of input and output examples we have, the better will be the efficiency of the neural network performance. To give you an example, any simulation that we do, let's talk about daylight simulation. Daylight simulation is an example of traditional programming where we have material specification, we have the geometry, and the software has the logic coded within its engine, and then we get an output. In such cases, we don't really need to use machine learning. Machine learning is used where we don't know how the output is arrived, but we need to find a correlationship between the two so that we can predict future output of future such events. In the same example, you guys may or may not know, but the daylight simulation results that we submit as a report, if at all a building is being green rated, the actual performance of the design after construction kind of varies a bit. It's never the same. Even if you construct everything down to the T with the right specification, with the right materials that you had used in the simulation, this variance between the simulated performance and the actual performance, there is no logic between, no established logic between these two at the moment. So that would be an example where machine learning could be used, because we know the simulated results, we have a grid of results, we know the actual as performing results, and then we can map the two, because the logic in between these two is missing. If I briefly talk about the difference between AI and machine learning and neural network, they are sort of one within the other. Neural network is the most specific algorithm which is used to solve machine learning questions, and machine learning is a specific kind of artificial intelligence algorithm. AI in the larger sense is anything. It could also be a traditional programming algorithm. It is anything that kind of mimics human intelligence or the way humans behave. For example, when we order food from Zomato or Swiggy, if we run into any delivery issues, we sort of go to the complaint button, we tap into it, and then we get a list of questions and we reply, and then accordingly we're directed to a specific query or a specific problem that we sort of make a docket of. That is an example of AI, which is not an example of machine learning, because that's an elaborate list of if-else statements, wherein if you select option 1, then you're directed to the next 3 options. From you pick one among those 3, then you're redirected to these many options, and sort of the map of those options is explicitly written down in code. So that's AI because it mimics a conversation, but it's not really machine learning. Machine learning would be any algorithm which sort of learns the patterns from the data and then can be used to predict the output for new data. For example, again, like I mentioned, if instead of the chatbot using if-else statements, if depending on what we type, if depending on the combination of the words, it learned how to detect our mood and then suggest what we should be doing, then that would be an example of machine learning. Neural network is a specific kind of algorithmic architecture where we, colloquially speaking, we connect a bunch of neurons and it becomes a neural network. But what it actually is that it's a series of mathematical functions of data being multiplied by factors, then divided by factors, and then passed forward or not, these kind of steady state questions. So neural network is a very specific example of machine learning. There are certain aspects of machine learning that are not neural network. I'll talk about them in the next slide. Examples of neural network in regular use would be the product suggestions that we get in Amazon or Flipkart when we are browsing, or even Netflix suggestion of what you should be watching depending on our previous likes. So it's learning through our interaction with the software. So it's kind of predicting our pattern of liking. And in a way, it's trying to second guess what shows we may like. And accordingly, it's suggesting that these are the ones that you may enjoy. You get that percentage of likeness. There are, like I mentioned, there are certain machine learning algorithms which do not use neural network. Some of those are called linear regression or non-linear regression, logistic regression, etc., etc. These do not use neural networks. These use other means to sort of predict the outcome of data points depending on how it learned from previous data points. Now, how regression is calculated may be a little too complicated for you guys, so I'm not going to get into the details of it. I'm going to give you another example, which will be easier to understand. This particular algorithm is called KNN, which is used to classify different data points. So let's say you begin with an input classification where you have category A and category B. Let's assume for the timing that these are just points in the XY plane. The moment you introduce a new category or a new data point, rather, not category, and you have to analyze and predict to which category this new point belongs, what non-neural network machine learning algorithms like KNN would do is that they would literally calculate distances to all the category points from this new point to all the categories A, and then find an average of them, and similarly calculate the distance to all the points in category B and find an average of the distance, and then it'll simply compare which average distance is closer or rather smaller, and then accordingly this will be added to that particular category. So it's a rather crude way, a rather rudimentary way of classifying different aspects. Of course, classification in terms of product suggestion or music suggestion, or even in case of architecture, wherein if let's say you like design A or design B, from the whole repository of designs, you are then suggested, since you like this kind of a design, probably you'd like design X and Y and Z as well. These connections are not actually as rudimentary in nature. These are rather more complicated. They involve a lot more variables than just explicit measurement of distances. Those can be taken care by neural networks, where the categorization is not done linearly, so to speak. There are more complicated mathematical functions can be used to execute the process. So in a way, apart from how the backend works, the other major difference is in accuracy, wherein non-neural network ML algorithms, if let's say if they are 70 to 80% accurate, employing neural network in such a case would increase the accuracy by at least 10% or so. As a thumb rule, there are outliers. There are always outliers. If I talk about the different types of learning algorithms, machine learning algorithms, then there are predominantly three types. The first one is supervised learning. The second one is unsupervised learning. And the third is reinforcement learning. Each of these methods, or rather each of these algorithms, have an example within machine learning, which doesn't employ neural network, and also has examples which employ neural network. Like I mentioned, the difference is in, but of course, the architecture of the process, but also in how accurate they are. Neural networks tend to be more accurate. Now, what are these three kinds of learning algorithms, and where and how could these be applied to architecture? Let's first understand the three types. In supervised learning, your input data is labeled, and with the use of the label, the machine can predict what would be the new data type. For example, if we use a bunch of images of dogs and cats, just a second. Yeah, of dogs and cats, and we label those images that these many images are of cats and these many images are of dogs, and we feed those images into a neural network with enough number of iterations, with the way neural networks understand images, it will be in a position after, let's say, sufficient number of iterations to predict if a new image, which will not be labeled because then we'll be using the neural network. For a new image, it can predict to a sufficient degree of accuracy if it is an image of a cat or a dog. Similarly, instead of cat and dog, we can also train neural networks with, let's say, images of Doric column, Ionic column, Corinthian column, these three. We can feed a bunch of images and then train the neural network in a manner that for any new image, which kind of is in the between, we're not sure if it's one or the other. Even in those cases, we can sort of run it through the neural network and try and understand what the network is telling us, because the network learns through the distribution of the pixels in the image, and consequently it can tell us which one of the labels is the new input most suitable to, or can be attributed to the most. In unsupervised learning, these labels are missing. Unsupervised learning is predominantly used for classification or clustering. In these, you supply a bunch of images. You don't tell the neural network if it is a cat or a dog. All you tell the neural network is that we need two kinds of classifications or two kinds of clusters. It may well be the case that the neural network will automatically classify it in a manner that dogs and cats are differentiated. But amongst the original set of images without the labels explicitly telling it cat and dog, it might be the case wherein it distinguishes it into two parts, wherein part one is light colored animals, part two is dark colored animals, or one would be animals which are furry, the other would be animals which are not furry. So Unsupervised learning in that manner is a little more difficult to control because there are no explicit labels, and we sort of have an indirect control in the sense that we can only tell how many categories we want. It will categorize automatically, and we have to interpret how or how the categories make sense. Now, in the case of cats and dogs, it's pretty obvious because we can sort of categorize it so intuitively. But let's say in case of pretty extensive data point, let's say we talk about Calcutta. Let's say we take each one of the 144 wards in the Calcutta Municipal Corporation and we tabulate number of households, number of hospitals, all the various parameters that are tabulated in a census, number of homeless people, etc., etc., area density, number of people with direct sanitation, number of households without electricity, etc. And then we want to categorize these wards into different categories so that, let's say, we want to devise a policy framework for them. Because there would be so many variables involved, dividing them manually becomes a really difficult task. In such cases, unsupervised learning can be used. So if you say, give me 3 categories, and then it will, depending on the distribution of the numbers, it will give you 3 different categories, and you can sort of then sit and interpret how the wards have been divided into different categories. More often than not, they end up making sense, where you'll see that part 1 has high density, however, has less amount of homeless people. Part 2 has low density, but has high amount of homeless people, so on and so forth. You'll end up getting such patterns extracted out of the data. The third kind is reinforcement learning, where we don't enter any data into it. It's basically, in the traditional sense, it is the machine learning type which mimics how we as humans learn the best. What does it do? It sort of gamifies the learning process, wherein you have to code an environment and you have an agent which has to navigate through the environment. And each time it makes a mistake, you deduct certain points, and each time it makes a right move, you give it certain reward. So you're punishing and rewarding, and iterate this very simple module enough number of times, it starts to learn how to navigate through that gamified environment. How would that be useful in architecture? I'll talk about that in a while. Yeah, so like I mentioned, supervised learning is good for classification and predicting trajectory of numbers, be it stock market prediction or like how we're going to quantify subjective opinions. Unsupervised learning is good for clustering and finding associations. And reinforcement learning is basically sort of making an agent go through a gamified version of a real world environment. These are just some examples of where these could be used. I would like to show you a short video of an example of reinforcement learning so that the process becomes clearer. Screen. This is, I've specifically picked a very rudimentary example so that we can relate to it. I've not picked any demonstration of self-driving cars. So yeah, as the video says, the snake head, so to speak, looks at the different directions, 8 directions, and then figures out how far is the food block that the snake has to go ahead and eat. And also simultaneously sees the distance between itself and the wall, and lastly also sees the distance between its head and its tail, because if you bump into yourself, you sort of get disqualified from the game. So as you can see in the initial iterations, since it has not been rewarded or punished, it tends to go randomly and not in the direction of the food, and then sort of hits the wall, crashes against itself. It's kind of a mess. It's like a child is playing with the video game without much cognizance of how it should be played. So if we sort of go ahead and go more towards the higher generations or the higher number of iteration, you'll notice that a pattern of gamification, or rather the pattern of playing the game emerges, wherein if it hits a wall, it's getting deducted points. If it's for each step, if it's not hitting a wall, it's getting rewarded. If it's not hitting into itself, it's getting rewarded. And through that reinforcement of reward and punishment, it is learning by itself, which is basically how at a very rudimentary level how dogs are trained, wherein you sort of punish the dog if it behaves incorrectly, and you reward the dog with, let's say, a chunk of food if it's behaving properly, and so on and so forth. So yeah, so as we get into generation 20 or so, it has become pretty good at playing the game, and sort of plays pretty neatly. Anyway, getting back to our discussion. The best example of the use of reinforcement learning, apart from self-driving cars, is in the game of Go. Now, the game of Go happens to be the most complex game ever designed by humankind, wherein the number of configurations of blocks that are possible is higher than actually the number of atoms in the entire world. So such is the number of configurations possible. AlphaGo is a reinforcement learning research that Google had undertaken, and they'd made Lee Sedol, who was at the time was the champion of Go, and then made the two play against each other. Some of you may remember that in the late 1990s or early 2000s, there were games between a computer and the world chess champion to basically see, or rather answer, the man versus machine question. There's a significant difference between the two. In those examples, the machine literally worked or played through brute force calculation. And what do I mean by that? For each step, it calculated all the possible steps which could be played from that step onwards, and it literally, using brute computation force, calculated all those steps and then sort of decided based on which would be more conducive. It decided to play a certain step. It's possible to do that in chess because the number of possible moves in chess is significantly lower than the number of possible moves in Go. Till now, we don't have enough computational power to use brute force calculation to play Go, which is why there has been a significant paradigm shifting difference in the use of algorithms. Now, instead of using brute force, Google used reinforcement learning, where through reward and through punishment, in the gamified version of Go, the machine ran enough number of iterations to extract patterns of play. And then using that intuitive pattern of play, it went head to head against the human champion. And it won, I think, 3-1 in a series of best of 5. And not only did it win, but it went on to play certain moves, which at the time didn't make much sense to the commentators. And they were sort of speculating that the machine has gone kaput, or a machine is playing gibberish moves. But only later on, when that move started to make sense, did the commentators, and in fact even Lee Sedol himself, realize how much of a genius it was in terms of the way the maneuvering was done. Um, Something similar is done in self-driving cars as well. This is a pretty comical image. I apologize for that. This is the best I could find at that moment. The vehicle becomes the agent, which has to navigate through, let's say, a gamified version of uh, the surrounding world, or the way the world is captured through cameras and motion sensing, etc. So the way this learns is that first of all, the vehicle, through all of its senses, renders the environment, or renders the state of the environment. And depending on the state of the environment, it decides a certain action, which would be how you place your steering, and of course the speed at which you are to navigate. And this is simulated in a virtual environment again and again and again, where if you're safe, if you're comfortable, and if you're efficient, then you get rewarded positive points. And of course, if you crash into another car, or a human being, or for that matter, violate speed limits, then you get punished. And once you run this iteration millions of times, along with highly equipped state-of-the-art tech to understand or scan the environment, wherein we can read a road signage which says that you have to travel below 60, which means that now in my algorithm I cannot go beyond 60. Such vision detecting algorithms, all of these things have to evolve simultaneously to an extent where such autonomous cars can finally be introduced to the business of actually going ahead and actually getting people to go from point A to point B. Now, it may seem like the design of a building is simpler than playing chess or even playing Go, but that is actually not the case. Mathematically speaking, if we talk about placement of rooms next to each other, or even placement of chips in a circuit next to each other, if you run the mathematics of how many ways in which those can be placed, you'll realize that, in fact, the placement of rooms for an extensive building, I'm not talking about a small residence of, let's say, 2 bedrooms and 2 bedrooms, a living room, and 2 washrooms. I'm talking about, let's say, a departmental building. Such is the complexity of the number of rooms, the variety in which the aspect ratio length is to width can be placed, arranged, the variety in which those can be mutually placed, and of course the variety in which those could be oriented. Such is the variance for even the most simplistic departmental buildings. If you run the mathematics, you'll know that it's way more complicated than playing Go or playing chess, which is why probably reinforcement learning has not been utilized in the case of architectural design thus far. But since it's at a very nascent stage, it's been only about 18 or 20 months that across the world people have started talking about AI in architecture. We expect this to be addressed and breakthrough to be made in this area as well. In let's say, I'm hoping by the end of this year we could have a pretty good idea of how it could be used. Now, if I talk about the use of supervised learning in design, which was, remember, the first kind of example where we had labels or numbers or texts which told the algorithm about which is cat or which is dog, or how could this be used in architecture? Of course, similar to stock market price prediction, you could use some of that in architecture as well if you could want to predict the price of housing from one place to the other. That is obviously one such example where it could be used, where for all the available property rate, you can note down its location, the distance to the nearest school, the distance to the nearest market, uh, what are the amenities around, what is the locality like, what is the average price around the locality, and if you tabulate all of them and you have enough number of data examples for a given city, you can accurately predict the property rate of a new property, and it has been done across the world. Uh, in fact, such a method is used by the consultancy firms like KPMG and Deloitte to sort of predict real estate prices. That could be one example. The other, which is more related to the design or the analysis of design, is that it could be used to quantify subjective feelings or quantify visual perception of a design or an urban scene. And the quantification can be sort of taken from the crowd or from the people or the users instead of it coming from top down, from the, let's say, the designer to the users. Now, how could that happen? This is the exercise that we are going to undertake tomorrow and the day after. So I'll talk about this. This happens to be the absolute tower designed by Mad Architects. We are also going to develop the Grasshopper script as a demonstration of how Grasshopper works of this particular tower. Now, what we can do is that we can make a script which is complicated enough to generate variations which, even though have the same logic, but have completely different visual output. And once we do that, we can get people, which in our case will be us, to basically rate each new iteration compared to the original design and get them rated as to how original or plagiarized they are. And then with that data, wherein how plagiarized or how original a certain iteration is, becomes the label, similar to cat or dog. And then we can take this entire ensemble of data and label and then train a neural network to predict the originality score or the plagiarized score of new design iterations. Now, how may this happen? First of all, of course, we have to have a mechanism to produce a variety of options. The script that I'll be sharing with you will have 12 different variables, controlling the size of the floor plan, the amount of rotation in the building, absence or presence of projected balconies. So you go from a perfectly extruded star-shaped plan to a perfectly, a rotated elliptical plan using the same script, wherein the plan sort of morphs from one shape to the other. However, developing a script to this complexity, where even the plan is morphing in shape, cannot be done in the 12 hours that we have. So as far as our script for the rotating tower in Grasshopper is concerned, we'll simply restrict ourselves to just rotation and variation of floor to floor height, etc., etc. We won't get into how plans get morphed from one shape to the other, because that's a whole different exercise. That's a whole different topic in its own right, which is morphing a geometry from one shape to the other. So once we have the variations scored, we can have, let's say, a list of such values where we have the numbers or the parameter values for each of the variables. And at the same time, we have the average originality score. So the originality score sort of becomes the label, where earlier it was cat and dog, cat and dog, cat and dog. Here it is, instead of being only classified into cat and dog, it has a it doesn't have a discrete set of options. It goes from 0 to 1, where 0 is absolutely plagiarized and a value of 1 would mean that it's pretty original compared to the original design. And in the case of cats and dogs images, these input values were the pixel values of the images, but here we will use numbers. And when I say pixel values are also numbers, which we are going to see in a while, or probably tomorrow. An image of 4 pixels would basically have 4 values, right? So it's an array or a list of 4 values. Similarly, here we have a list of the numbers which make up these iterations. So for this, let's say this iteration, if the originality score is, let's say 0.9, over here in the list, we will note down the values corresponding to this option, all the values for these variables, and the originality score of 0.9. And then using these values, we will train the neural network to predict newer values, or the new originality scores of newer variants, which have not been previously evaluated or scored against. And of course, once we do that, once the neural network is trained, then we can keep varying the slider values, arrive at a new variant, and then export it into the neural network, and it will tell us what is the originality score of such a new design variant. So in other words, what this does is that given that we have only a few, which is being shown here diagrammatically by the magenta dots, if we have only a few variations rated, or only a few data points, we can train a neural network to sort of mimic the entire solution space, so that even if we want to know the performance or the originality score or the subjective evaluation of an option which is somewhere in between, which has not been rated thus far, it can do so because it sort of automatically approximates or appropriates the entire solution space. Right. Now, after the discussion on supervised learning, now let me get into the business of style transfer, and we will get into more details of supervised learning tomorrow, where I'll specifically talk about how a neural network maps numbers from input to output. Those I'll explain tomorrow. Today, we're going to concentrate on style transfer, where we're going to use a ready-made pre-trained neural network to sort of carry out our tasks. Right. So if you ever Google style transfer using neural network, or neural network that works with images and things like that, the term that will keep bumping into time and again is called convolutional neural network, which is neural network in regular sense. It's called convolutional because it deals with images instead of numbers, and B, because it applies a filter called convolution and another filter called pooling to sort of understand and extract, let's say, the geometric features or the visual features of an image. Now, how do they work? What is convolution? What is pooling? Let me discuss those. Just give me a second. If we just talk about a given image, for example, this one, which is it says mentions the letter 2, or one could argue it's just a black and white snake wrapped around itself. Who knows? The point is that by itself, we just look at the pixels. It's just white, gray, and black. White, gray, and black. So 0, 150, and 255, right? Just by itself, if you just look at individual pixel values, it's impossible to predict which is what, because it doesn't make any sense. No pattern emerges out of it. Pattern emerges out of pixel distribution only when we get into, or rather represent an image as a derivative of individual parts of the images. And what do I mean by that? Let me just explain it through examples. Like I mentioned, two things happen as far as the machine seeing images is concerned. We employ, or the neural network employs, two different kinds of maneuvering tactic. One is convolutional filter, the other is pooling. First one, let's first discuss about convolutional filter. If you look at, let's say, this particular part of the hand, which has the nail polish, and if, let's say, for argument's sake or for explanation's sake, if you look at pixel values of just a 3x3 grid with these values, there are ready-made filters which have been researched through the years, which are used then to multiply the pixel values with these given filters. Now, it may just appear that, I mean, why do we need to multiply these pixel values with such convolutional filters? I mean, why do I multiply the 0 with -1, 64 with 0? Why have such filters, right? It is seen that once we multiply the pixel values with certain ready-made filters, certain, let's say, stylistic or geometrical aspects of the given image become clearer. So, for example, when the pixels on the left image are added a convolutional filter of this particular chunk in the middle, it gives us an output like this, which basically means this particular convolutional filter, these numbers, are multiplied to extract the edges of a particular image, where you can see these edges are being extracted. Similarly, there are other convolutional filters which are used to extract the change in texture, the change in color, so on and so forth. You name it, there are a number of filters to extract those certain values. You may ask how this was devised, why such numbers. I am not sure how these were devised, but I am pretty certain that there have been PhDs after PhDs in the MITs and the Stanfords, and I'm 100% sure in your computer science department as well, on how to better devise filters which can A, make the process faster, and B, using the same filter, we can extract multiple information. For example, this one only extracts the edges. How can we use the same filter to extract multiple information like edges and texture and color, so on, and other such features? I must add one more thing, that the use of such filters may seem completely abstract to us. It looked abstract to me when I began my journey in the use of AI. But I'll just draw your attention to the use of 3D modeling tools. Like, if we go back 200 years, just 200 years, and if we told a layman that we would be representing your building digitally, where you'll see a smaller version of it, where one corner of your house will be at 000 The other extent will be at, let's say, 20 meters by 30 meters by 40 meters point. To that human being at that point in time, it would have appeared rather abstract and vague without him or her understanding why do we even need to do it, because I can talk about building my house, I can get people to build my house, I'm getting my house built, why are we doing it? So many a times such concepts are sort of brought to fruition or initiated through a rather extreme or vague or random hypothesis, and only when it works out do more people sort of get into figuring out a more efficient version of it. Which also means there are more number of hypotheses which do not see the day of light, do not get sort of distributed across the world. There are more failures than successes. But again, this is just one of those things which I guess worked out and which is why we are here right now discussing it. The other is called pooling. Now, pooling is something which helps in reduction of computational time and also simultaneously helps in enhancing the features. How does pooling work? Again, let's take this 4x4 pixel matrix. What pooling does is that it divides it into constituent parts. Let's say, for example, into 2x2 matrices. And then from each of those individual matrices, it will pick up, let's say, the highest pixel value, and then re-represent this 4x4 into a smaller representation of 2x2, wherein the highest pixel value of each of the divided matrices is being represented. So in a way, you sort of go from 4 into 4, 16 data points to 2 into 2, only 4 data points. So there's a significant reduction in the computational time. Now, again, one may think that since we are reducing the actual representation of pixels, probably we're going to lose some finesse or lose some resolution, right? But as it turns out, that is not the case. Even though the size of the image reduces, the feature which is extracted through the corresponding convolution filter gets enhanced when we work with pooling or when we apply pooling. That is because if again you, again we go back to this example, you'll notice that the highest pixel is taken in corresponding to its local neighbors, right? So in a way, the local differences are in a way controlling which particular pixel value is taken forward. So over here, if let's say you had certain gray patches, because there were black patches or white patches, depending on which you see as highest, be it white or black, the gray is sort of rejected and you only pick the white bit for that part or the black bit for that part, and which is why you get a clearer image with more enhanced features. So this, get back to this image, this convolution and pooling, this is repeated again and again and again to extract a feature or two from that particular image. Now, how depending on this extraction of features or this reduction of image size, how does the computer identify if it's being, let's say, shown 2 fingers or 5 fingers or 4 fingers? This I'm going to explain tomorrow as I explain supervised learning in more detail. Right now, because we're using a ready-made neural network and we're not discussing per se about training a neural network, which we're going to do tomorrow. Now let's restrict to the use of style transfer. Because style transfer is the most appropriate introductory exercise once you sort of get acquainted to the use of neural network. After that, explanations of the other couple of concepts which I've left for tomorrow, those will make more and better sense to you. So what is style transfer? As the slide explains, it basically takes the content from a content image and the style from a style image and sort of combines the two, wherein the style from the style image is rendered using the geometry or the content from the content image. So in other words, if you see look at the example, this particular painting, the smaller tile is the style image. This random hatch, solid hatch, is the content image, and through execution of style transfer, we get such an output where the geometry of the content image, however simplified it is being sort of articulated using the style, which includes color and texture of the style image. Multi-style transfer is basically the same, wherein instead of one style image, you're picking two style images, which is why you see that there's a combination of the black and white etching and the painting texture, the stubbing texture of this particular painting, and there's a combination of the two. So in other words, the content image provides the geometry which sort of acts as the petri dish onto which the style from the style image or multiple style images are sort of mapped and sort of painted onto it, for the lack of a better word. So what are the various things in that architecturally speaking we can speculate using style transfer? The first example would be that we can sort of interstylize drawings, architectural drawings, be it plan, section, elevation, or even 3D views. This particular example combines the plan of Ahmedabad Di Gufa by B.V. Doshi and the Sabarmati Ashram by Charles Correa. So when the content image is B.V. Doshi's plan, which is predominantly circular and rather organic in nature, and on that we apply the style of Correa's rather rigid orthogonal plan, you can see that the articulation of the spaces has automatically been pixelated. And not just that, it hasn't just stopped at a micro level, stopped at converting the curves into pixels, but it has by itself. Remember, I or we won't tell the algorithm to pick the specific points. It does it by itself. It has also understood the style of these corridors, these long corridors, and sort of mimic those by extending these lines, these rectilinear false dummy wall-like lines. On the other hand, if we apply it the other way around, the rigid orthogonal plan sort of gets metamorphosized into circular and curvilinear pieces. Granted, this particular output, even though visually interesting, is more gibberish in nature. Which is why we keep repeating that the entire process is rather speculative at the moment. This would need a certain amount of post-processing to clearly go ahead and say that this is a floor plan that could actually be used. So for a given content image, which in this particular example is the floor plan of B.V. Doshi's Ahmedabad Di Gufa, if you combine the same content image with different style images or style plans, of course, the output would be different from one case to the other. For example, on the left side, it's picking up Corbusier's oblong thick walls. And we've already seen the one in the center column towards the right. It's mimicking the style of a Palladian villa, where it is automatically picking up the visual feature that makes a Palladian villa so iconic, apart from being symmetrical, and the visual feature being the staircases which lead up to the uh, uh, closed spaces. So in a way, it's fun, it's cool, but also at the same time, the fact that it can pick up these signature elements is both beautiful and startling at the same time. As to, we're not explicitly telling the algorithm or the neural network to pick up the signature style, but it just goes ahead and does it anyway. Similarly, if we keep the style image the same, and let's say only vary the content image, where I'm not even varying the overall, let's say, the overall shape of the block. I'm just varied the gradient in which the block has been hashed, and that itself, as you can see, will yield different kinds of output. Because again, remember, there's a component of pooling where the pixel value is picked depending on the values of the corresponding pixel. So there's a comparative nature in the foundation of how pixels are picked and how features are extracted. So here, because our local or localized variation is radial in nature, obviously the output also has certain very bold radial signature radial feature to it. Similarly here, because the gradient is rather linear in nature, we get sort of these brush strokes which are also linear in nature. At the moment, this process, apart from such speculative exercises, or let's say to visualize an architect's design in the form of or in the style of another architect, apart from such exercises, this particular method could directly be used in our design workflow, be it academic or professional, in generating artistic renders of concept diagrams, where again, just for demonstration's sake, to sort of demonstrate that it works with a very dumb content image as well. So obviously it is going to work with the smart content image. I've taken the same random block and you can apply different styles and it'll render the concept diagram or the concept hatch in completely different artistic ambience, so to speak. So again, depending on the content and depending on the style image, you can extract these diagrams. And keep in mind, such image production is very vital in terms of communicating your design intent right now, not only with your professors, but later on, initially to your boss, and then even later on, probably to your client. So these tools and these skills will obviously be useful. Now, some of us would be great at such stubbing. Some of us could be good at such painting. Some of us could be good at such mixed medium. Some of us are not good at any one of them. So it's useful for all of us, and it need not be restricted to just color, right? It could also be applied with black and white style images. What it also does is that it works across various scales, from, like we just saw, concept diagrams to plans, and now to figure grounds of the urbanism scale, not even urban design scale. I'm talking about urbanism, where, as an example, if I've taken Noli's Vienna figure ground map, and onto that, you can obviously apply the style image of, let's say, another place. In this particular case, it does happen to be Vienna style image. And as you can see on the output, it starts visualizing or speculating how the fabric will look once it realized. So you don't really, for fast visualization or for speculative discussion between different options, you don't really have to go to the burden of rendering these in either Photoshop or taking realistic renderings. You take reference images, you know that such will be the distribution of material across the fabric, such will be the color of greenery across the fabric, so you can start speculating how it may look from one option to the other. This was a fun exercise where Venice's style image was projected on Vienna's figure ground image. And so as I've been mentioning, it extracts features for each pixel by comparing it to the neighboring pixel. What you will notice is that in the content image, which is Vienna's figure ground diagram, patches which are white are rendered as water, or patches which are water in the style image are somehow correlated to, by the neural network, correlated to the white patches in the content image. Now, why does this happen? We can start speculating on this as well, because within here in the white patches, there is no significant difference to its neighbor. And within the style image as well, there is no significant difference with its neighbor in the blue patches, which is why it automatically starts to correlate the, let's say, uniform patch of style to uniform patch of content image, and then so it sort of maps the water into the white patches of the figure ground diagram. This, of course, eventually will lead to certain very fundamental question. One being the question of computational power equity. The two exercises which we are going to do would be pretty easy to compute, as in it won't take much time, but for larger or more extensive neural network training, the computing power could go from a week to a month's time. That's how long it actually does take. So there would be a question of equity, wherein one may say that innovation in the domain of AI, be it in design or otherwise as well, may be eventually restricted to large organizations or large companies who have that sort of capital to invest. And so smaller organizations or smaller practices may not have such a leeway of capital to invest in computational power to sort of speculate in new developments, and as in how we invest more time in AI, the world community does, more things will be established, which would mean that establishing new things or innovating new things will take that much more effort, which again sort of brings or sort of highlights the discussion of equity of computational power. The amount of computational power you'll need right now to make an impact is significantly less than what you need 2 years down the line, because a lot more people will get into the domain of AI. The other question, and I guess there's a more significant and more legal question, is the question of authorship, which is if the two input images are taken from someone else, do I get the authorship of the output, or does the authorship remain with the original authors of the two input images, or does it get divided between the three of us? And if it does, then in which ratio does it get divided? Is it 1/3, 1/3, 1/3? I don't know. Also, there's a question of authorship being labeled to the computer. How am I the author of an image if I've merely selected few images which get combined? I don't know. Probably because I know how to handle the neural network, one could say that I am the author, but am I actually the author? These are just certain philosophical questions that collectively the world of design and art making and architecture would have to answer. In this case, food authorship will be divided into 4 parts: me, the machine, and the authors of the 2 original images. We don't know. We need to speculate and um, sort of discuss what would be the solutions of these. So as far as the tools are concerned, for today's exercise, we are going to use something called Google Colab, which is a free sort of free Python notebook platform, which connects pre-existing libraries which deal with neural network with cloud computing, which will be necessary to execute style transfer. We need free cloud computing because the GPUs of our laptops or our PCs, the personal ones at least, are not strong enough or powerful enough to execute these tasks within, let's say, acceptable time periods. What may take 10 minutes in the free Google platform may take, I don't know, 3 hours in your system, even if you have the highest of high end of NVIDIA graphics card. So what Google Colab does is that it can help us work with various libraries which are released in various forms, and then we can execute them while the execution happens in its own, rather Google's own free cloud system. I'll explain which library is related to which particular part of the code and explain all of that. And I'm also going to talk about how does style transfer work and how does, or rather how do iterations affect the overall output and other aspects of content versus style once we move on to the execution of the task. And of course, style transfer can be applied to transfer style between plan to plan, section to section, paint to solid hatch, like I've just demonstrated, pattern on elevation, 3D view to 3D view, map to map. And I mean, there's no limit to this. If you can think it, you probably can. You can think of a combination. You can go ahead and mix the style and the content of those 2 images. Having said that, that concludes the presentation to begin with. If you and I'll take your questions. And then we can move on to using style transfer as an exercise onto the Google Colab notebook. So yeah, any questions? I can start taking questions. It could be need not be related to style transfer. It could be related to any other speculation as far as the use of AI is concerned. Okay, I suppose there are no questions at the moment.
Okay, that was a wonderful, very, very informative session, Mr. Manu. Thank you so much. I thoroughly enjoyed it, learned a lot of new things which I didn't know about. It was very informative. So for the next session, you are planning to do hands-on certain exercises related to style transfer. So
Yes,
the students will have to install anything in their computer, or will have to get access to it?
no, not right away. I had shared a Google Drive folder link with you.
Yes,
I have
that has been
uploaded
posted.
I have uploaded the Google Colab file that we're going to use in that folder. I'm sure every one of us have Google accounts, right? So we can head over to Google Colab website and directly start using that particular notebook. We won't need to install anything at this moment.
Okay, so I request students to please check that you can access that. Please click on that and see that you can actually access that folder and find out if you can get into Google Colab. If you have any issues with that, please point it out now.
Ma'am, I tried it. It is working properly.
Abhi, do you have something to say?
Yes, ma'am. It's working properly, ma'am. I can download it.
Okay, perfect. Wonderful. Thank you for pointing that out. Thank you. Professor Gupta, would you like?
Yeah, I just had a small question to Architect Joy. Like,
Yes.
yeah, I found that during the morph discussion of the morph, changing of the plan form. So I have found that that has been applied in tall building designs. Okay, so I was just thinking, do you also can we also incorporate the structural system through it? Because as I have gone through research papers, I have found that morph operation and how the star shape moves on to a maybe triangle and the structure is connected and how it actually simplifies from that hexagonal plan or maybe a star shape plan finally to a rectangle or a square or a triangle. Okay, so are there various layers? I just out of curiosity, I'm just asking because I have seen these in research papers how it is being executed.
Yeah. Thank you for the really interesting question. Yes, it depends on how and on which tool one is making such shapes. If at all one is using parametric tools, because the overall shape is being guided by, let's say, one initial shape on the left and another shape on the right, let's say from a rectangle to a star shape. And because these are being in a way averaged between the two, so rectangle becomes slightly star-like, more star-like, and then completely star-like. So because there's an average between the two, the points on the rectangle, which let's say are used to anchor columns or through which columns go, those points also vary as the rectangle varies and becomes a star shape. So those points also vary along with the morphing of the points. And so those changed points or those displaced points are then used to sort of make the columns. And then based on those columns, beams are made accordingly. So if one is at all capable of working on parametric tools, extracting the logic of placing structure, at least conceptually, is not difficult. Then, of course, it's a question of having the right kind of structural engineer to sort of, stick their neck out and who is on board to make such a structure. Yeah.
Thank you very much. So it's very interesting, and I would love to join the next session. We are not at all experts in these, but okay, learning with the students would be, I think, easier for us. Another point was the picture in that image that was of turning torso.
No, ma'am. This is.
But it is created. Okay, there is a glitch, I think.
Sorry, I lost connection for about 10 seconds.
Yeah, you lost
I got your question, ma'am. This is not the turning torso. This is Absolute Tar D by Mad Architects. I'll type the name of the project in the chat window so that you can get the absolute spelling.
I personally wanted to mention one thing, which was I found the names of the plugins to be extremely confusing, because I could never think as looking at that name plugins. I mean, brilliant. As a Bengali, I would say such Jingri and Ilish are just brilliant to name.
So I've noticed on their website that they have all kinds of names. So hoop snake, elk, gecko. So I'm like, yeah, Bengali. I ought to give Bengali names, right? And what better to sort of use that fish as a Bengali? So that
Absolutely.
was.
I think you made Bengalis proud there, right there. You
Yeah.
did that.
Thank you, ma'am.
True, true.
Another thing, ma'am, I would like to mention is that this whole business of morphing is also done extensively in facade design as well. So,
Yes.
whereas in the case of tar, it's linearly moving on top of each other, so the rectangle becomes a star. In the facade, it moves laterally, so
Yes.
you have a rectangle, and then in stepwise manner, it becomes a star. So their structure isn't so difficult because you basically have to take chunks out of the material. So I mean, otherwise it can remain a flat surface. So in one case, it sort of goes on top of each other, and in the other case, it sort of gets placed next to each other. But in
Next
both
to-
cases, it sort of um, it, it works at the very subliminal level of identifying series, like series of arches. Even here it's series, but within the series, instead of exactly the same repetition, it's similarity of elements. So yeah, if we simply put the rectangle next to the star, our brains won't connect them. Only when we have enough number of average elements in between them will our brains be able to understand the smooth gradient between the two.
Actually, that is
Can
pattern
I
generation. Yeah.
can I add something on it?
Sure, sir.
I'm Professor S.P. Bhattacharjee of the same department.
Yes, sir.
This is quite new things for me. Actually, yesterday I was discussing with Priyanka that whether I should join it or not, whether this should be tangent to me or not. Anyway, this is very tangent to me, but still I'm understanding something. But what we are discussing, the Sumana ma'am also told, and your this form generation. This is very interesting in the sense we have seen from the structural point of view, a tall building will actually have the lot of windows. There is a background sound. There is a background
Okay.
sound.
Okay.
Can
Okay.
somebody switch off? So due to the wind, there is a huge load generated. That is transverse load generated. And we all know that the windrows of a particular place is not going to be constant. Maybe the summertime, the wind comes from southeast to northeast, and the winter times, or maybe other times, it is some other way. So if we have a typical one type of the laminar kind of a structural, your form, then probably it won't going to optimize the total amount of load, that is the shear that comes in the base or whatever, and the moment in all the joints. So probably this kind of the typical turning and typical kind of what probably the initiation of the Calatrava in his design of the turning torso, that it won't have a laminarity in any, specific direction. It will have a laminarity in the all the 360-degree direction, and that will going to optimize the total amount of wind load annually, not in a particular session. So to do that optimization or the specific that kind of the form generation, I think human brain cannot do that. It is now probably we have to go with this new type of artificial this logic and whatever. This is my just a comment on that.
Yes, sir. So, uh, of course, there are CFD tools which can simulate the nature of wind flow across, or rather around a building, to sort of understand what sort of load it's imposing, if there are micro eddies being formed, or if there are local entrapments being formed. So those can be connected to, let's say, different iterations of the of a tower design, and then probably based on that, the final shape could be determined. So even in the conceptual framework of what just ma'am suggested, of let's say a rectangle getting into a star, how much of the rectangle becomes a star, or does it becomes a complete star, or does it become or does it become half of a star? Even those decisions, those macro decisions, could be taken by such load calculations as to. So it's basically a combination of, let's say, a visual signature with performance of various kinds. And yeah, but we won't be concentrating on such optimization exercises because yeah.
But it sounds. I mean, when you start your this first lecture, it's actually opened up a lot of opportunity for us. Actually, I mean that is the thing. Anyway, it is very wonderful start with. We are very much looking forward to have a, good understanding and this new domain. Thank you very much.
Can I just have a small question or maybe a sharing of information? As you talked about this authorship and all and rights, etc. That means the intellectual property rights kind of. So and also you showed us that at least 2-3 big companies can actually handle such information and all. Do you think that at individual level can it be taken up for small projects and?
Well, as far as I'll make a distinction between optimization using parametric tools and the use of AI at this moment, because when we talk about AI, we have to A, collect data, and then B, train a neural network to execute a certain function. Whereas optimization using parametric means would mean that the optimization algorithm is pre-existing, be it CFD simulation or daylight simulation or structural load simulation or even energy calculation. As far as the optimization using any of those calculations is concerned, of course, anyone can do it as long as one has the technical prowess. Any standard laptop will be able to execute the computational load. As far as AI is concerned, collecting data does take a lot of time, but it's not impossible. Also, training neural networks is not impossible, but what would be impossible at an individual level will be to generate new kinds of neural networks. So, for example, we keep hearing about art being generated by AI, or someone has composed music through AI. Those paradigm shifting new introductions will be difficult to do at an individual level simply because of the amount of resource and experimentation and tinkering that one needs to do. But with pre-existing neural networks, which we're going to see, for example, using numbers to predict new things, those can be done at an individual level at any time. I mean, it takes about a week to conceptualize something and have enough amount of enough amount of data. And as far as collecting data is concerned, if it's not directly from sensors or something as objective as that, if it's subjective in nature where we have to get people to review it, then it's just calling people up, sending them the link, following them a couple of times, probably irritating them a couple of times and getting the review done, and that's about it. Yeah.
Actually, so our master degree students do such exercises, and actually they can also use it as you talked about the project on safety of women or whatever into the streets and all. So the master degree students can really do that.
Yes, ma'am. Of course. Yes.
Yeah.
Yes.
It's wonderful that Professor Gupta pointed that out. In fact, initially when we were interacting, Joy, we were discussing this, that we also have a PG course and the students could actually see a different aspect. Of course, today we are here to discuss with students of architecture, undergrads, and we have a different perspective for the workshop. But yeah, definitely the things that you're talking about, the applications in, say, urban heat island mapping or urban design and other urbanism projects that you were talking about, I think our Master of City Planning students would find it immensely interesting because they try to attempt to do these researches and they can apply the tools that you are talking about. And in fact, we were discussing that. We can definitely do that for our master.
Later, yeah, we can do that later, yeah.